So let's go back to this density operator in real space and also in momentum space as we defined last time. This rho is an electron density operator defined in real space, which is nothing but this psi dagger psi defined in the real space. But the more important quantity is the Fourier transform density operator, rho as function of q, where q stands for this momentum transfer. For example, if we create an electron-hole pair and the momentum transfer between electron state and the whole state is given by q. If you sum over all possible electron-hole pair, but this is not necessarily electron-hole pair near the Fermi surface, but in general, k is not restricted to just the momentum close to the Fermi surface. But of course, we will pay more attention to the momentum states close to the Fermi surface, but here, this is simply just sum over all possible states. And this we will see in just a moment represents the density fluctuations operator for electrons. And so we try to use this density operator, especially rho of q, to re-express the Hamiltonian of electron gas interacting by Coulomb. And this is the Hamiltonian for that Coulomb interacting electron gas that we started a long time ago by Hartree-Fock, but we don't take the Hartree-Fock approach. Instead, we should rewrite especially the potential energy term in terms of rho of q. But this can be achieved because you could simply just rewrite this 4 fermion operator by taking advantage of the anti-commutation rules between 2 fermion operators, C, K, and C, K dagger. So we could simply just interchange these 2 operators as we like. So again, by using this anti-commutation rules, we are able to rewrite this, the 4 fermion term in terms of this expression, where the middle part comes from this anti-commutation rules between 2 fermion operators. One is C, another is C dagger. Good. So you could try to play this anti-commutation rules at home. And then we have 2 terms, right? So the first term, the second term. The first term is to sum over this Kronecker delta function and get rid of one of this momentum sum, which is you sum over k, and by plugging k as k prime plus q, and so you cancel this minus q here. So therefore you get C dagger k prime and C k prime. Right? Okay. With a minus sign here. And the second term carries a plus sign, which contains 4 terms. Okay, 4 operator. The first 2, C dagger k minus q, C k, and the second, C dagger k prime plus q, and C k prime. So if you know the definition of this rho of q, okay, and the first term, or the first pair is nothing but rho of q operator, and the second pair is the rho of minus q. Because the sum over k and k prime are separately down, so you could simply just encircle this 2 summation. And the red gives you rho of q, and the yellow rho of minus q. See? So the spin indices are implicit here, so I don't bother writing the spin index, because when you sum over k, apparently there's a spin S associated with this electron carrying momentum k, and when I sum over k prime, there's S prime. Spin indices included, and S and S prime runs from, say, up or down independently. All right? So remember, this rho of q defined here should include sum over spin, right? Sigma. As I already emphasized, that this electron density includes, this kind of electron hole pair for both spin up species and also spin down species. And so, in other words, this should also carry a sum over spin. To be more precise, so of course, we should have the spin indices here. To be more precise. Okay, so if I include the spin indices back to the summation, what I get is this, which is what? Which is minus sum over k of k, which is a number operator, which is the first term. And the second term is now becoming this rho of q, rho of minus q. But what is the meaning of this rho minus q? So we can go back to the definition of this rho of r. So rho of r is the electron density operator in real space, and this is actually a real quantity, which means that this is given by rho dagger of r, because the electron density operator is actually the Hermitian operator, which leads to the eigenvalue, which is given by electron density, which is, of course, a real quantity, because electron density can be measured in the laboratory, and it's a physical quantity. Any physical quantity that can be measured should be real. Okay? And therefore, rho of r plays the same role as rho dagger of r. But this condition immediately tells us that rho dagger of q is nothing but rho minus q. Okay, so this is your homework. Prove it. So you come from this condition that electron density operator should be Hermitian, which means that rho is actually the same as rho dagger. And from this condition and the Fourier transform between rho of r and rho of q, you immediately prove that this rho dagger of q is nothing but rho minus q. All right? So in other words, you simply just put a minus sign in front of the q of rho of q, and you get rho dagger, which is the Hermitian conjugate of rho q operator. As a result, you could simply just use this, Hermitian properties of a density operator, and you can rewrite this Hamiltonian in terms of the very familiar form, sum over q, 2 pi square over q square, rho dagger of q, rho of q minus n. And by the way, so if I write this rho of q, rho minus q in this order, this is the same as rho minus q, put it on the left of the rho of q, which means that if I interchange these two operators, I got the same result. And you can show that this, I don't need to assign this to your homework problem, but you could, immediately see that, density operator is a Hermitian operator. So you can show that this is the same, okay, which is rho dagger of q and rho of q. Okay, so of course you can ask, what happens if I just interchange these two operator. So you could check this, kind of identity that it doesn't matter if I interchange rho and rho dagger. Okay, so I take this identity for granted, right? So you could prove that at home. Good. So now we have derived this Hamiltonian for Coulomb interacting electron gas in terms of the density operator, as we plan to do. So now you could really see these interactions between different spin species in this new form. Because, as I mentioned, this rho or rho dagger operators include both species, right? So I can simply just decompose this in terms of upspin density operator and downspin density operator for rho dagger and also for rho So the Hamiltonian has this, row dagger row kind of form, but this form could be further decomposed in terms of different spin-spin interactions. So you can very clearly see that this includes spin interactions among the same spin species and also among different spin species, right? So you could simply just expand this product, right? So there are 4 contributions. So I don't want to repeat this. Row dagger up, row dagger down, row down, and row dagger up, row down, plus row dagger down, row up. Okay, so this solves the difficulties from this Hartree-Fock approach, because in the Hartree-Fock, the electrons interact only with the same spin species. But here we have all different kinds of spin-spin interactions. When both spins are pointing up or pointing down, or one up, one down, or one down, one up. It's a complete form of all possible spin-spin interactions through this density interactions. So in particular, this kind of opposite spin interactions, which is absent in Hartree-Fock approach, but it is present here. Okay, so absent in Hartree-Fock approach, but it appears here. Okay, so in other words, this kind of a density operator saves the troubles that the Hartree-Fock approach is facing. But we will see later that this kind of a language, or the basic operator, is probably the correct. Okay, and we will see in just a moment that this will lead to 2 very important phenomena. The first is called the plasma oscillation phenomena, and the second is the screening of Coulomb interaction, long-range Coulomb interaction. And we will just derive these 2 results one by one. Okay, so any questions so far?
Yes, what is plasma oscillation?
Okay, so I will explain to you just in the next few minutes. But in one word or one sentence, this is just electron density operator, which oscillates in time. Okay, so this is a periodic, like simple harmonic oscillator kind of motion for electron density. Okay, and which comes purely from quantum mechanics. And we will just derive this Heisenberg equation motion for such a density operator and see that rho of Q really oscillates in time with a characteristic frequency called plasma oscillation frequency. And this phenomena has been observed in many, many metals, like 60 or 70 years ago in the mid-20th centuries. And the observation of the plasma oscillation in metals really give us a confidence that this is the correct language. Okay, so we could derive this plasma oscillation frequency from this formalism, and we can compare our predictions of this plasma oscillation frequency with the experimental observations, which is quite in very good agreement, okay, between the theory and experiments. Yes?
And number 2, why don't we consider short-range Coulomb?
Yeah. So the screening of a long-range Coulomb interactions, which means that this Coulomb interaction is actually short-range. Meaning, if we use this language of density operator for this system, and we are able to show that the Coulomb interactions between any 2 charged particles is actually short-ranged. It's not long-range. Therefore, we cut off the long-range Coulomb interactions. And we will get back to this after this plasma oscillation phenomena. In other words, the Hartree-Fock theory cannot get the plasma oscillation, that's for sure. And the Hartree-Fock failed to screw in the long-range Coulomb interaction, that we have demonstrated. So now, based on this new basis, we are able to solve these two problems simultaneously. And that's the power of this electron density operator. That's a starting point. All right? So any other questions? Good. So let's take a short break. When we'll come back, we will start to address this plasma oscillation phenomena. So let's start the first derivation of plasma oscillation phenomena, based on this Hamiltonian in terms of the density operator that we just derived a few minutes ago. So let me just remind you what this plasma oscillation phenomena is about. So remember, we have talked about this a few lectures back, where in ordinary metals, electrons are moving around the positive charged ion cores like this. The electrons feel this attractions from this ion core, so this negative charge electrons tend to move close to the ion cores, but they overshoot, so that the net charge surrounding the ion core becomes negative, because there are many electrons, much more. The necessary amount of the negative charge get close to this ion cores, but then immediately the other positive charge ion move slightly towards that kind of a negative charge cloud, so to actually compensate this kind of a additional negative charge. But this is again overshooting, because now there are more than enough positive charge ions get closer to the negative charge cloud. So the net charge becomes positive, and this processes actually goes back and forth between the net negative charge situation and the net positive charge situation. So, and there's kind of a harmonic oscillator kind of behavior going between these two overshooting scenarios. And so that's kind of a hand-waving argument to see how this density operator can actually fluctuate back and forth with a periodic kind of motion. But this phenomena comes precisely from quantum mechanics, okay? Because from quantum mechanics, you know that any quantum mechanical operator is actually, in Heisenberg picture, is a time-dependent function, right? So you can solve this time-dependent, say, Heisenberg equation motion to get the time dependence of this Heisenberg operator. So we know that in general, the Heisenberg operator satisfies this Heisenberg equation motion, and the Heisenberg equation motion tells us that if you take the density, this any operator, the partial derivative with respect to time, and multiplied by minus IH bar, and this is given by the commutator between the Hamiltonian and that operator, right? So this operator can be arbitrary. It doesn't necessarily to be this density operator, but it applies to density operator as well. But then whether this will lead to some periodic motion is a question. So suppose that I'm lucky when I take this first derivative density operator with respect to time, and by evaluating this commutator between the Hamiltonian and the density operator, I can get a closed form, which is given by the prefactor times this density operator itself. Suppose I can derive such a relation, then this immediately tells us that this rho of H is actually is kind of a periodic motion in time with the characteristic frequency omega p. But of course, this is just assumption. So we need to derive such relations by evaluating this commutator. And you will see in just a moment that at the first order differential equation in time, this is not true. This is not the same as a constant prefactor times this precise the density operator itself, but a more complicated form. So in order to get this periodic motion and extract this information of this frequency, we need to go to the second derivative, which means that we need to evaluate the double commutator. So we will get back to this in just a moment. But let's try and pretend that we are able to get this relation. Before we can do that, let's just formally introduce this electron-hole pair excitation operator, which we call the speed dagger. Remember, this is related to this density operator, right? So K and K minus Q. So if you sum over all this, this is given by rho of Q, right? So let's just build up our operator method and try to evaluate this commutator, okay? But before we do that, so let's just construct the electron-hole pair operator and see the relation to this kind of a density oscillation or plasma oscillation physics. So there are two regimes to be considered. One is the long wavelength or low momentum transfer limit. Another is the highly excited high energy processes. So this long range kind of oscillation or the low energy limit lead to the plasma oscillation. But the high energy processes will lead to the single electron-hole pair excitation. Okay, so this is a conclusion. So we first introduce this single electron-hole pair operator, B dagger, and we can demonstrate that in the high energy limit, this is actually probably okay up to some approximation. But when this momentum transfer is really, really low, small, and we are dealing with this low energy excitations, which means that it's kind of a low temperature excitations, which is what we are interested in that case, then this B dagger, which creates a single electron-hole pair operator, cannot be the answer to this Heisenberg equation motion.
Professor, yeah. When you write the Heisenberg equation motion, I think the rho in the Q space, right?
Yes.
But if in the Q space, the omega P will depend on Q or not. That's my frequency.
We will come back to this, all right? Okay. But you could evaluate this equation of motion in any space. I mean, this Q, rho operator could be in real space or in momentum space, whatever space you like. But I just choose the rho to be in the Q space. You cannot stop me from doing this. Good. So let's just define this B dagger, which creates the electron-hole pair excitation in a many-body system at a ground state psi. And remember, this is the many-body system, which means that we have many, many electrons and many, many ions. So we will come back to this many-body nature of this phenomena later. Okay, but remember that this is the many-body system, and suppose we know the ground state, which is given by psi, then the Hamiltonian acts on this psi will give you epsilon 0, which is the ground state energy, multiplied by the same states. But now let's try to create excitation, which means that this B dagger operator, which creates electron-hole pair excitation, acts on this ground state, which will lead to the increase of the energy by amount of epsilon B. But still, this kind of a B dagger acting on this ground state psi is actually the eigenstate of the Hamiltonian with a different eigenvalue, which is epsilon 0 plus epsilon B, which means that this is just excited state above the ground state. And let's try to derive the relation between this Hamiltonian and this B dagger operator and see what it leads to. So if I simply just manipulate these two equations, I can get this commutator between Hamiltonian and the B dagger operator, which is given by this excitation energy epsilon B times B dagger. So this is really exciting because you can see that the similarity between this and this, right? Suppose I evaluate the equation of motion for B dagger, and I can almost get this closed form, right? Because epsilon b is just a constant, okay, independent of anything. So suppose I, evaluate this equation motion for this B dagger operator, and I get this. But unfortunately, this B dagger is not what we want. If this is just a single electron hole pair excitation, consider a different type of problem, okay? Remember this rho of Q, sum over P, C dagger, P minus Q, CP. So the density operator, rho of Q, is not the same as the single electron hole pair excitation. But to demonstrate this, let's just check this kind of commutation relation. Suppose B dagger operator is given by this. Then we could evaluate this equation motion and see what happens. So if I define this B dagger as C dagger P plus Q Cp, and this tells me that this is the process of a single electron hole pair excitation, P plus Q. So let's just calculate this commutator, because we like to solve this Heisenberg equation motion for B dagger. So this is just the first step, because we know that this B dagger is not what we want. But let's just try from the simplest case, which is a single electron hole pair excitation. And you could easily evaluate this commutator plus sum over Q prime, P plus Q minus Q prime, P minus plus Q prime, rho dagger prime plus rho Q prime, P plus Q prime plus Q, Cp minus dagger plus Q, Cp. Okay, so I leave this to you as another homework problem. Derive it. Okay, so to really study the heart of the solid state physics, now we need to really have this experience in evaluating this commutator between the Hamiltonian and the operator of interest. So here, the operator that we're interested in is B dagger, and we like to compute this Heisenberg equation motion and solve this equation motion for B dagger, and therefore we have to evaluate this. Okay, so the way that we evaluate this commutator is just to expand this Hamiltonian, and you simply just use the anti-commutation rules to simplify all this commutator. And the connected term, when you evaluate this commutator, will give you this difference in energy of excitation. And the potential energy term leaves the more complicated, many terms written here. And you could simply just play this anti-commutation rules to convince yourself that this is the correct result. So we will, start from here and try to argue that under what conditions can we say that the correct operator that allows us to solve the Heisenberg equation motion is a single particle hole pair excitation operator. And if not, can we make an approximation that allows us to solve this Heisenberg equation motion? And is it the same as this Heisenberg equation motion for rho of Q? Of course not, okay? Because we need to sum over all possible momentum P to get a density operator. But this is closely related to the plasma oscillation, as we will see in just a moment. So let's take a short break. Let's continue. As I mentioned, suppose this B dagger is what we want, which is not. Let's just pretend that B dagger is what we want. And we could evaluate this commutator between the Hamiltonian and this kind of a single particle hole pair operator, C dagger P plus Q, Cp. And when we finish this calculation, we get this kinetic energy term and the potential energy term. And suppose that there's no potential energy term, and there's just this kinetic energy term, and this is almost what we are looking for, because suppose only the kinetic energy term contributes, then this is nothing but what? Epsilon b times c dagger b plus q and cp, which is some constant epsilon b times this operator itself, and therefore this plasma oscillation is related to epsilon b. But this is too good to be true, because of course there's a potential energy term that will contribute to this commutator, but under some assumptions, approximations, we can neglect this potential energy term. And what is the assumption? Well, the assumption is that when Q is large, when we have very large momentum transfer like this, and we excite very high energy particle hole pair, and in that case, this energy difference, kinetic energy difference between P plus Q state and state P is much larger than the potential energy term. Okay, suppose I have excited the electron in the inner shell state, and I can kick this electron out of this Fermi sphere to this kind of a space, to the universe, so that this electron hole pair energy is really large. And in that case, this energy difference between state P and state P plus Q is huge, right? And when that kinetic energy difference is huge compared to the potential energy term, and I can forget about the potential energy term. But this is justified only when the momentum transfer is huge, which is not what we are familiar with, that this electron hole pair is just the states close to the Fermi surface. No, this is very far away from the Fermi surface. We have a very high energy particle hole pair. Excitations is created by this kind of operator. In that scenario, we could safely neglect this potential energy term. And therefore, the commutator is approximately, remember, this is not exact. This is only approximation. Approximation is given by the kinetic energy term. And when that happens, we can more or less see that this kind of a Heisenberg motion can be solved. However, this is not what we are looking for, because this physics is at the single electron hole pair level. So this kind of physics is a single high energy electron hole pair excitation, which has nothing to do with the plasma oscillation. Remember, the plasma oscillation occurs only at very low temperatures, and the momentum transfer is really small. Okay, so it's kind of a small perturbation to the zero temperature ground state of a many electron system. And so this is certainly not the physics that we are looking for, even though it looks attractive that we could solve this Heisenberg motion if we assume the kinetic energy is much larger than the potential energy. But this is not the correct physics that we are looking for. This is a different physics, which is related to the high energy single electron hole pair excitation. Okay, so single high energy electron hole pair. So we must go to another limit when Q is really small. When Q is small, then the trouble arises, because the potential energy term cannot be neglected, as I mentioned. So you cannot get this closed form as simple as this, because we have a messy term arises here, which makes this solving for the Heisenberg motion impossible at the first order in time derivative. However, suppose instead of evaluating this commutator without summing over P, suppose I sum over P for this B dagger operator. And remember, when you sum over P, this C dagger P plus QCP, this is nothing but rho of minus Q, right? And this is what we are looking for, this density operator, and the equation motion for density operator. However, if I plug in this commutator between Hamiltonian and this rho of minus Q, I get at the first order, I get this. So the potential term vanishes, okay, magically. And this is another homework for you. Suppose I evaluate not just a single electron hole pair operator, but I sum over all possible momentum p, which is nothing but the rho of minus q. So if I evaluate this commutator between the Hamiltonian and rho minus q, I get the contributions only from the kinetic energy term, but not from the potential energy term, because all the potential term, when you sum over p, get cancelled, and you need to show that the cancellations really is there. But is it what we're looking for? Of course not. Can anyone see why this is not what we're looking for? Well, the obvious reason is that this energy difference carry the factor p dot q, right? Because this is what epsilon p plus q minus epsilon p, which is p plus q square minus p square times h bar square over 2m. So you cancel this p square, you get p dot q h bar square over 2m. But the trouble comes when you sum over p, right? When you sum over p, this energy difference, when you sum over p, it's not the same as just a constant which is independent of momentum times the rho of q. So if you carefully compare these two expressions, and the right-hand side is what we are looking for, a constant prefactor times the density operator itself. But unfortunately, we don't get this simple form. Instead, we get a complicated sum over p, and inside the summation, you get, so let me just write down this summation right here. You get sum over p dot q, c dagger p plus q, cp. So the summation over p, affects this prefactor, also affects this moment indices of the operator. So this prefactor is not the momentum independent prefactor. It's included in the summation, and therefore it is not a constant that we're looking for. So to get the oscillation frequency, what we need to show is that after this commutator evaluation, you get the constant prefactor multiplied by the density operator itself. And if we can show that, then this constant is certainly related to the oscillation frequency. But unfortunately, it is not. And the reason why it is not is because there is a p dot q involved here as a prefactor, which is not a momentum independent. So you need to sum over p, where this summation over p involves both the prefactor and the operator. So you cannot separate this prefactor from the operator. And therefore, at the level of the first time derivative of this density operator, we don't get what we want. So what can we do? Right? Of course, we know this kind of overshooting physics, where the density of electrons oscillate between the more positive charge and more negative charge limits. But at the first order time derivative, the Heisenberg equation motion cannot lead to the closed form. So what can we do? The only option that we have here is to go to the second time derivative. So the hope is that by going to the second time derivative of this operator rho, we could evaluate this double commutator. And we hope that we can make some approximations and simplifications so that at the end of the day, it is going to be h bar square omega p square times rho of q. Approximately, again, approximately. And the good news is that it can be done, okay? And that's how we get the plasma oscillation frequency, is by going to the second time derivative of the density operator and evaluating the double commutator between the Hamiltonian and the density operator. And we can make some approximations and to actually separate this prefactor from the operator itself, so that this is a constant, which is precisely what we are looking for. So to summarize, suppose this B-DAG operator takes this just a density operator rho of q, then at the first level, in time derivative, we are not able to get this closed form. So we need to go to the second order in time derivative in order to achieve this kind of a density fluctuations. So remember this rho of q. In a Heisenberg representation, take this time dependent. And we could take the first time derivatives rho of Q and to get this equation motion, but we cannot get a closed form. But we could continue taking the second time derivatives rho, and we get a double commutator. And fortunately, we are able to get this constant omega p out of the second time derivative of a rho and a double commutator here. Okay, so that's the plan, but we haven't started yet. Any questions so far? Yes?
How about the q squared term in this one? How about the q squared term in this?
Q squared term. Yeah, of course. There's a q squared.
Also the 2 in the denominator.
Yes. Yes. Of course, the q squared term up here, but it's, well, again, you can add this term, right? So this is h bar squared over 2m, and also plus sum over p, 2m h bar squared, q squared, c dagger p plus q, cp. Which one will get cancelled?
The first term, no here.
This term?
2 in the denominator.
Oh, yeah. Yes. Yes. Okay, thank you. But you do get what I'm trying to say, right? Okay. Suppose the prefactor depends on momentum, and we cannot say that this is just a constant, because it involves the summation over p, which is not what we are looking for, apparently. Of course, there's a q squared term, but this will only complicate the situation even more. So you got two terms. One is sum over p with p dot q, another is sum over p q squared. So, of course, you cannot, by summing over these two terms, get this simple form like this. But here is a important lesson to be learned, that suppose we consider only the single electron hole pair excitation, and this excitation could be in the eigenstates of the Hamiltonian only if this momentum transfer is really, really large. And we will go back to this later, right? So this is the high energy single electron hole pair phenomena, which is, again, a very important phenomena, but we need to distinguish between the high energy excitations and the low energy excitations. So the high energy excitations is a single electron hole pair excitation, but what we're looking for is the low energy excitations. The low energy excitations will lead to the plasma oscillation and density fluctuations in a periodic motion like this. And later we will divide the potential energy term precisely into these two categories, the low momentum transfer limit and high momentum transfer limit. And here in the high momentum transfer, the physics is a single electron hole pair excitation. But when Q is really small, you get the collective motions of a plasma oscillation. So there is a really sharp distinction between the collective excitations and a single particle Hall excitation. So this plasma oscillation physics is a collective phenomena, which means that all the electrons participate in this kind of density fluctuations in time, which is certainly at the level of the low momentum transfer limit. Okay, you can imagine that if the momentum transfer is really, really tiny, and electrons here and electrons over there sort of know each other, and then they dance together. It's kind of a duet, duet. It's kind of a dancing pattern that you get your partner, and and your partner dance together. Okay, but by contrast, this high energy single particle Hall excitations is just a single excitation event, where this particle Hall pair has nothing to do with the other particle Hall pair excitations. But in this low momentum transfer collective region, that everybody knows everybody else, and everybody is involved in the dance together. It's like in a ballroom that you have many pairs or many couples that they are dancing together in a very large ballroom, and there's a music and everybody dances in the same way, and that's music corresponds to this oscillation frequency. And this involves all electrons, and they sort of know each other's dancing pattern and they dance together. But in the high energy limit, they're just a single electron hole pair excitation. That's all. So in the low temperature limit of ordinary metals, what we are interested in and what we really observed is this many-body collective excitations, that electrons are dancing together in a periodic way, that there is a characteristic frequency associated with that collective motion, and this collective motion is called plasma oscillation. So we are almost there. That just that we need to evaluate this double commutator, and we could really derive this omega p here. And omega p depends on this average density of your system and electron mass and so on. Okay, and so depending on different average density of your metals, this frequency varies. And we could sort of using some detector by hitting something to the metals, and we could just detect the electron energies after scattering. And then the difference in this two energies precisely fit this kind of a quantum energy of plasma oscillation, which is integer multiple of h bar omega p. And h bar omega p is a single energy of a plasma, energy unit of a plasma. And plasma is again a quantized energy, which we call this quasi-particle, which comes from, again, this kind of excitation, which takes a quantum unit of energy. And in the real metals, we could see this kind of quantized plasma energy, which is an integer multiple of h bar omega p, and which match this kind of a scattering intensity of a normal metal hit by electron beam. Perhaps we could stop here for now. Any questions?
So Fiona, for the small q, your plasma frequency is independent of the q, right?
Yes. So we will see that under some approximations, this omega p is a function of your average electron density and your electron mass. That's all.
And I think in general the plasma frequency could be dependent on q, right? Like the phonon.
No, this is different from the phonon phenomena because, of course, in phonon, the energy depends on this phonon momentum, right? But the plasma oscillation frequency, as we'll see later, that depends only on the electron density, and it has nothing to do with momentum. Of course, we, make some approximations, but if this approximation is okay, then we could really see that this omega p depends only on the fundamental constants.
Can I say, if you have a small q, yes, I think omega p doesn't depend on q. But if I increase the little p, there's some dispersion.
That's precisely this phenomenon. You see, this is precisely the point. If you increase the q, then every term depends on q. You see, this is why I'm telling you this.
But you will not call this large q, you call it large q it's not a collective excitation, you call it a single electron hole excitation.
That's right. But imagine that we are not in the small q limits. Of course, everything depends on q. Even if this is not a single particle hole pair event, but still, this omega p is not a constant anymore. So we really need to go to the small q limit when q is really, really small. And next time, we will evaluate this double commutator and make some approximations in the small q limit. And we can simplify this double commutator such that this is proportional to this omega p squared times rho of q, and plus other terms which we don't care in the small q limit. Of course, this is not exact, but in the small q limit, this is okay. And this is not, fancy theoretical predictions. This is the real phenomena that you can check in your laboratory. And this has been observed over and over again in many low-temperature laboratories for many metals. So this phenomena is real. Okay? So we are talking about all the phenomena that can be observed in experiments, and we would like to understand why this phenomena occurs and the reason. And the reason for this plasma oscillation to occur is precisely because of quantum mechanics and many-body system. Okay? So just quantum mechanics alone that cannot explain this kind of a collective motion. We need to include the ingredients of many electrons in there. So remember, this Hamiltonian contains, infinite number of electrons, okay, and their density operators. And by quantum mechanics, under certain limits, this kind of motion describes many, many electrons, all the electrons. So this is not, the phenomena that you can understand from the single particle quantum mechanics. This is many particle quantum mechanics. And next time, we will see this many-body quantum mechanical phenomena by evaluating this double commutator. All right, so this is something new. And you may learn this kind of phenomena, but I'm sure that most of you have not studied why this phenomena come about. And you will learn this, next time.
Professor, is this so-called charge density wave?
You could say that this is a charge density wave in general, but there are many different charge density waves in solid-state materials, and this is in a particular form of charge density wave, which is the density fluctuation in time. But the charge density wave that you are talking about is mainly for spatial variations, a spatial charge density wave that varies in space, but we're not particularly interested in their time dependence. But here, we are more interested in this time dependent of this density fluctuations. Of course, they vary in space, but what we call here is density fluctuations or density oscillations is actually in time domain. In that sense, we cannot call this CDW, but CDW is a term, the jargon reserved for the spatial inhomogeneous charge density fluctuations. You can call this charge density wave in time. Good. So if there is no further questions, please read the corresponding chapters in Kittel's second book and also in David Pine's book on elementary excitation in solids. And in both references, you will get this kind of equations and formulas that I wrote here. Okay, so I think this is not, technically speaking, this is not an easy task. I understand that, especially if you have not, computed this commutator before, and you will find this kind of a headache or a trouble. But you need to get through this at least once in your lifetime. If you are an experimentalist, you need to evaluate this just once, and you can forget about this. But if you're a theorist, you should be familiar with this calculation because it will haunt you and become your nightmare. So you need to conquer these calculations if you are a theorist. So I hope you'll find this interesting. And on Wednesday, we will talk about this double commutator. There's still 15 minutes. Let's proceed a little bit further, and we take a short break. And after the break, I will introduce the concept of the random phase approximation. 有一些强关联的材料。那在 低温的时候，在基态 ground state 的时候，会有这种 many body state， 就是它们的电荷是有在空间上有一种 fluctuation， 有个 pattern， 那我们叫 CDW charge density wave。OK， 那在高温超导还有很多其他的材料里面都已经有出现过。好，那为什么会有这个呢？简单讲，就是因为系统要minimize energy， 那同时有电子的电荷的跳跃，同时有 spin 跟 spin 的磁性的 interaction， 所以是 magnetic 的 interaction 跟 strong correlation， 就是说库伦排斥力以及 electron hopping 这几种力量在互相抵消或者说互相竞争的时候的一种妥协的产物。你可以想象它是一种妥协的产物。electron 如果没有任何交互作用的话，它希望能够变成金属。OK， 可是呢，如果有磁性在里面，或者说这个库伦作用力、排斥力太强的话，那 electron 就不会变成金属，就变成绝缘体。可是这两种势力，假设在某种模糊地带的时候，它可以让你的 charge 是有一种像条状形状的这种 pattern 会出现，就是在一个范围里面，它可以让你有点移动，可是呢，你没有办法整体的 electron 可以有 hopping 的作用，它会间隔一个小段的空间的区域，那这段区域呢是 charge 是没有分布的，所以说有没有有没有有没有这样 ，OK， 那为什么要有跟没有呢？那没有是干嘛呢？当然就是因为有磁嘛，有磁或者说它的库伦排斥力太强了，所以它会 favor spin 会反平行，好，所以就是一种妥协之下的产物。你有兴趣的话，可以之后有一些 reference 可以看一看。
老师，可是我这样讲的话，你电子就没有办法后平，那为什么又变超导，就变成电子可以局限在某个范围区？
如果有 CDW 的话，就不会是超导态啊，这的确是这样子啊。但也有说超导态跟 charge density wave 共存的，好像是在某特殊的材料里面是有的。那为什么会这样？当然，它的超导就不是那种均匀的超导，也许就是局部的超导。But that's another story. So by the end of the lecture today, let me just introduce a very important approximation called the random phase approximation, or RPA. This is the approximation that we applied when we evaluate this double commutator. Remember, the electron density operator in real space is related to the Fourier transform by this equation, and we could sort of expand this Fourier series in terms of q equals 0 and finite q. Remember that the q equals 0 component of the electron density operator corresponds to the average density of electrons, and we have proved that already, right? Okay, but there is another finite q components of this Fourier decomposition where q can go to arbitrary value, and this is a reason why we call this random phase, because q can be arbitrary. Therefore, this phase appearing in the Fourier decomposition is arbitrary, it's random. Okay, so that's what we call this random phase. But apart from this random phase for q finite component, there's another important approximation in this RPA, which is this one. So we assume that q equals 0 component is actually much larger than the finite q component. In the realistic metals, as we mentioned, that there's a density fluctuation, but that fluctuation is really tiny or small compared to the average density of electrons, which is kind of a constant m bar, which is rho 0. And in many metals, this is the reality, that electron density more or less stays a constant, but on top of the constant average density, there's a small fluctuations in space, and the small variations spatially corresponds to this finite Q components of this density operator. Because this is precisely what you guys are asking about, this charge density wave. This is nothing but a charge density wave. Why? Because this electron density, in terms of the finite momentum decomposition, is given by this Fourier sum, where you can consider this as sum of a different component. So suppose I have only one momentum Q, which I call this Q1 involved here. So this is a charge density, because if you plot this term, it shows a periodic pattern in space. Okay, so after what? So you tell me Q goes to Q plus 2 pi, you go back to the same value, right? Okay, this is nothing but a sine and cosine. You know what the sine and cosine is. These functions are periodic functions, right? So therefore, this is a sine Q dot R plus cosine Q dot R. So if you plot this component Q1, you get this kind of periodic pattern in space, right? So what is the period of this 2 pi over Q? Something like that, right? Okay, so this is... but this is just one of terms. Of course, there are other components, say Q2. Again, for Q2, you get different oscillation frequencies, right, in space, and so on and so forth. So the Fourier sum is nothing but you sum over all possible charge density waves, right? So this is a particular charge density wave with a period associated with the Q1, and this is another charge density wave associated with another period associated with Q2, and so on and so forth. And this rho of R is a sum over all such a possible charge density wave in space. So I don't know what is the resulting pattern looks like, but what we can see is that as you increase the value of a Q, this density fluctuations actually decreases in magnitude. Namely, the higher harmonics of the density fluctuations, the lower the amplitudes we expect. And that's the assumption behind this random phase approximation, that the zeroth order is the leading order in your electron density. As you increase the value of a Q, the magnitude of the density fluctuations get reduced even further, so that the small q dominates this density fluctuations. Okay? Of course, this is a continuous summation over q, so still this is kind of a summing over the small q terms of this Fourier decomposition. And we still don't know this really, what it really looks like, but more or less it will be dominated by the small q terms. So that's what the random phase approximation is telling us. But of course, whether this is true, we need to confirm that. So this is just assumption. Okay? But the good news is that this assumption works very well for ordinary metals, because in ordinary metals, this is precisely the density fluctuations look like. Right? So you get almost uniform background charge distributions, and on top of that, you get small variations. And that small variations are coming from the small q components of Fourier decomposition. And to evaluate this double commutator, we need to rely on this random phase approximation. And also this RPA will also lead to the screening of a Coulomb potential, which we will talk about this after this plasma oscillation phenomena is derived. So I guess that's enough for today.